analysis on a F1 car, the forces that act on it and the factors. In third week, you did analysis on a 2D object, which was airfoil. And in this mini project, we'll be going ahead with F1 cars. So let's begin. And also I'm recording this video so that you can watch it later if you have any problems. We'll start Workbench. I hope you have installed it from the week one. So like these are the various analysis systems on which we can do simulation. And here we will be doing fluid flow of air over an car. So we'll select fluid flow fluent. These are the 5 steps that we have to do to get a desired result. Geometry, in which we create a geometry. Mesh, in which we do meshing. We create we divide the object into tiny pieces to perform the calculation. In setup, we provide details and boundary condition. In solution, we find the solution using iterative techniques. And in result, we show the result using various graphs and figures. So let's begin with geometry. Here it is starting Space Claim. Space Claim is the CAD engine of ANSYS. Like this is like if you have installed the newer version of ANSYS Fluent, you will be getting Space Claim as a default geometry engine. But for this mini project purpose, we will be using the older, which is Design Modeler. Space Claim is better than Design Modeler, but for our specific purpose, Design Modeler is pretty easy for beginners. So we'll be closing this. We'll right click. Yeah, we'll new design modular geometry. Here it is showing the status starting design modular. So this is the interface of design modeler. These are various planes X, Z, X, Y, Z. It shows 0 part and 0 body because we have not done anything. Like in design modeler, we can create a car by scratch also, but this video will get scratched. So here I will be importing a geometry of car, which I have also shared in the chats. So yeah, it has been imported. We'll generate this body. In all of the ANSYS software, the status is shown at the bottom left corner. So like this is our car. Here it is like in a standing position. So first we'll try to rotate it. We'll create body transformation, rotate. Yeah, we'll select first body. So Yeah, select all. We'll apply it and we'll rotate it by 90 degree. As you can see, like we have to rotate it by Z axis to get a car, horizontal car. So we'll select this axis. Yeah, so it is showing how it will be shown. We'll generate it. So here we have our car. So yeah, it is done. Now we will create an enclosure. Enclosure is a like boundary under which our enclosure is a domain under which we calculate our values. So we'll go with create tools enclosure. So like we can create an enclosure by default settings. So this is how it will be shown. But in aerodynamic analysis, to we need to calculate the values behind the car. That is the wake formation and stuff. We don't need like, this many space above and below, and also not sideways because it is not the airflow is not much affected here this far. So we'll change these values. So six and then -5 will be 0.2. Then draw list 0.5 works. This is not strict dimension. You can change according to your own. So we'll generate it again. So like this is a better geometry of enclosure. Uh, the bottom part is also very less, and we can also see the enclosure. The rear region. So this is also done now because like this is a symmetrical structure. Like you can divide it by uh, which axis? YZ axis to get a equal car. So we'll try to divide. We are dividing because when we divide, it is easier to calculate because it is bilateral symmetry. So create slice. We will select slice by plane, and it is YZ. So it is red and blue. Red and blue is XZ axis. So we'll select this. So yeah, we'll generate. So I think I selected the it is blue and green, so it is YZ. Next slide, sorry guys. Yeah, so it is now divided by the XY plane. Uh, yeah, actually no. We will delete this for now. Like we have to create a hole. We will, yeah, we have to do a Boolean operation. In Boolean operation, we can divide one body from another. Our target is this. Apply. Um, we will select by box plan. Yeah, so we'll generate it. So as you can see, it is now only one part and one body. Previous it was seven part and seven bodies. So now it is only one. It is now only a box with a hole under it, which has the shape of a car. So now we will do the slice operation. We know it is by XY plane. Let me check. That is by XY plane. We'll generate it. Now two bodies are created. We need only one body, so we'll suppress this. So now, as you can see, we got a geometry. We'll be doing simulation on this. So we are done with the design model part. We will close the design modeler, and you can see there is a tick here. Now we'll go ahead with mesh. We'll wait while the mesh start. So yeah, we'll create mesh. We will generate. For now, it will be mesh will be generated by the default settings. So our meshing is done. We can see details here. Here it is showing number of cells. A cell is like a triangular quadrilateral structure, which you can see. Yeah, so like there is currently 3,277,000 cells, but like for in the NC student version, only 500,000 cell is allowed. We cannot do calculation with cells more than that. So we will try to reduce the number of cells here. So we will do with the we'll reduce the smoothing. We'll generate it again. We can see the status of machine here. Yeah, so our machine is done, and here we have a much coarse mesh, but we still have to reduce it. So we'll go with Z-axis. Hi, Saffron.
Hi.
If you have any doubt, you can ask. You can just see the recorded video later, and you can. I have already shared the step file. You can do calculation from it. So yeah, I'll be going ahead. Yeah, we have to reduce the mesh size of the structure. We'll go ahead with mesh sizing. We will select some faces. This is just an option to select some faces. Selected our faces. We'll apply. We will reduce the element size to 0.1. We have to set behavior to hard. We will generate. If you guys have any doubt, you guys can ask. And if you are watching a recorded video, you can contact any mentors. So yeah, as you can see, the mesh is very coarse, and we have also reduced the number of cells to like 347, which is less than for 500,000. So we can go with our calculation. But like I would like to like distribute the cells better, so like I will also reduce the size of these cells. So we will be doing again slicing. This will apply. Same 0.1 and behavior to hard. We set the behavior to hard because in soft option, the ANSYS can manipulate our settings to give us a final mesh. But here we don't need a final mesh because if we use final mesh, it will go beyond 500,000 limit. So we are setting behavior to hard so that ANSYS will not change our settings of 0.1. We'll generate it again. You can see the progress. So as you can see, we have a very coarse mesh, which is fine. We can go ahead with calculation. Like we have also named these faces. We will be doing that. We will set our view as isometric. Face selection option. Select this face. we have selected our walls. We'll do create name collection. We'll name them as walls. So you can see here name selections. We have a wall select. We have named these faces walls. We'll do again same thing. This is a symmetry of face. Symmetry. We have this and the selection. Name selection. Right. And we have also I will to select the card we cannot select the card by face selection option because when we do this we will get a for the face this face gets selected, so we will do this box select box and a card will get selected. Name selection we will name it just surface. So yeah, we are done with the meshing. Before closing, we will select mesh and update. So mesh has been updated to our workbench. We'll close this. So as you can see, we have also tick here. Now in setup option, as I already told, in setup option we set the boundary conditions. So we'll be doing the 3D analysis, double precision for better accuracy. And in solver process, I'll be selecting force. Solver process is basically the number of cores in your CPU which will be using, which will ANSYS Fluent use to perform the calculation. I have a 6-core CPU, so I'll be using 4. You guys can use 2, 4, or even 1 as your computer specification. This is the main ANSYS Fluent screen. Yeah, you can see this is a card design. This is inlet. This is outlet. This is our first we'll be doing unit. We'll be changing the unit of velocity because we are doing velocity and pressure calculation. Mostly in CFT, we do velocity and pressure calculation. We'll set it to kilometer per hour because that's the realistic speed of air in real life. Set this. So yeah, we have also defined gravity. Gravity is in, like as you can see, is in minus y direction. So we'll use 9.81. And these are set up in and the model which we'll be using is viscous, and in viscous we'll be doing k epsilon realizable k epsilon model. Okay. The by default air is selected And if we want to do analysis in different fluid, we can also set it. So yeah, we'll set the boundary conditions uh, in inlet. We will set the velocity magnitude to 50 kilometer per hour. Apply. It is applied. We will set the outlet. Uh, yeah. So if we have to set the outlet pressure at 0, this is by default option, but if it is not by default set to 0, we have to change it. Okay. And for lift and drag calculation, as you can, as you guys are studying in the week 1, lift and drag are calculated on a reference area, so we have to calculate drag parameters, reports, projected areas. Projected area in car is in x direction, so yeah, in x direction over the surface compute. So yeah, this is a projected area. Close this. We'll set it in reference values. We'll change the area to this projected area and set the velocity to the velocity this 50 is done. Okay, it is all right. Okay, we will be doing method. The method by which ANSYS fluent iterate the technique. This is similar to like methods. Like there are many different methods to solve linear equation and equation two variables, like Newton-Raphson method, and also like there are very there are many methods to solve equations. So this is similar to that. Scheme coupled. We will do higher order term relaxation to get a result faster and set the relaxation factor to 0.25. Uh, all these, all the rest of the things are by default. Now we will be doing reports. It is we will do report definition. We will do track force. We will track coefficient. Report output is drag coefficient, and the drag coefficient will be acting in x direction, so x100 into console over the surface. Okay. Drag. I will be doing drag force. Force into console. All things are same. Now lift. Lift is acting in y direction, so it is also correct. Surface. Console over surface. Close. So this is also done. Now we will initialize. Like you will be learning the iterative technique in third semester. Yeah, so Yeah, in third semester we will do standard initialization because in every iterative techniques we set we first initialize the solver. This one will set the standard initialization compute from inlet. X velocity is -50. Yeah, all things are correct. We'll come initialize. So our initialization is done. Now we will. So we will not be running our calculation in this. Uh, uh, in setup option, we only set the boundary condition which we have already done. So we'll close this. Close current. So Enclosure is a very heavy software, so it may sometimes hang, but it's fine. So, so whenever you do access Fluenter simulation, close all the rest of the softwares. It is a detail. We will set the number of iteration to 500. All things are correct by default. We'll calculate. So, see, this is a match. This is our residuals, x velocity, y velocity, and z velocity. This is a lift force. This is a lift coefficient plot. This is a drag force plot, and this is drag coefficient plot. It will take a lot of time. So you guys can do all this iteration later. I have already done it, so I'll just stop this. I'll use. I'll just show you the calculation after the iterations are complete. I have already done that. So yeah, after the iterations are complete, you will get a tick at the setup option. this one, and after that you will do solution, and in solutions let it load. Yeah, so this is a basic view. This is our enclosure. This is a hollow of car. We can also see a mesh edges display. Yeah. This is our mesh. And for the roads, sources, yeah, to get the lift force over the surface. And now, for the drag force, we'll get this. So our drag force is this. Our drag force is minus 62 Newton because the car is in X direction. So drag force acts in the direction opposite to the motion. So the drag force, the magnitude of drag force will be 62 Newton, and the coefficient, yeah, coefficient will be this. And if we want to find lift, we can also see. So the lift is 100 Newton with the lift coefficient is 0.92. I'll show you this later. I'll first show you the results after the iterations are complete. Yeah. I've already made this. I'll delete it and do it again. So in this result option, we will see the results. We will insert. We will see the contours of velocity contours. Location inlet variable, like velocity. We will set the contours to 100. We'll apply. Uh, Apply. We will set it at symmetry. Apply. Yeah, so this is the contour of velocity. So as you guys can see, blue is like zero velocity and red and yellow are like high velocity comparatively. So like close to the boundary, we can see like there's a blue line there. This is due to the boundary layer condition, which says the fluid stops at the boundary. So this is that. And you can also see the velocity is very high above the like there's red and yellow region, so velocity is pretty high. This is because the air tries, we design the car in such a way that it pushes the car to the ground so that it doesn't get lift off at high velocity. As you have already seen, the lift force was negative. So this is same, and you can also see like there is blue line here. This is the wake formation, the eddy formation. Here the boundary layer gets separate. So yeah, we will insert vectors, velocity vectors, locations, symmetry, deselected, objection, apply. So yeah, you can see this is the vectors, velocity vectors. Uh, as you can see, the red is high velocity and green and blue are very low velocity. The fluid comes here at the speed of 100. It gets it speeds up due to the curvature of the body surface. And here we have our wake formation, eddy formation. That is the drag force. So we can also generate streamlines. So these are our streamlines. Uh, Flow of the velocity over the car surface. You can see you can also increase to like 250. Fine. Set it to we will also see our pressure controls. We'll deselect streamlines, pressure, location at symmetry, contours, 250, apply. So this is a pressure surface. So when the air hits the car surface at the front of the body, you can see there is a very high pressure. This is red and X red it is like 165 Pascal. So that is because our velocity decreases to zero suddenly, and by the Bernoulli's theorem, when velocity decreases, pressure increases. So yeah, this is the same. And you can also see the pressure is low here compared to the above to force the to push the car downward to the ground. Similarly, we can also do the contours, vectors, and of pressure. All of these are same. Yeah, we are also done with our FD post. we'll just so that was it for this simulation. If you guys have any doubt, you guys can contact any of the mentors. And the recording of this video will be saved in chats. You guys can simulate the aerodynamic analysis using this recorded video. So that is it. If you guys have any doubt, you can ask me. If not, I'll just